Hi everyone, I'm Avery, coming to you sorta live from Portland. I'm a production engineer at Meta, where I've worked the past few years on configuration management. Thousands of services at Meta use configuration management, so it's important we change that configuration reliably. Today, I'll talk about how we reliably change configuration at scale. And my dogs may leave some commentary in the background, as they have a lot of thoughts on the matter. The dogs may be a close second, but my favorite part of this talk is going through how we tackled the problem of the multiple comparisons problem. While recorded, my talk is meant to be interactive, so during that multiple comparisons problem section, and others, I may pause to give you a chance to work through the challenges yourself, as I really appreciated when my professors did that during my classes. Without further ado, let's dive in. My talk will detail a story spanning several years, covering how my team exponentially grew coverage of a protection mechanism for one of our most critical developer workflows. With a 25-minute talk covering that large a time frame, there's going to be some lossy compression. I'll be glossing over some large and important projects we delivered to accomplish this goal, and won't have the chance to cover the other protection mechanisms we built. That said, I will give you a curated 10,000-foot view into the process we took to scale this protection mechanism, and dive into some specifics of challenges we faced and overcame. I'll cover configuration management at Meta, the inherent scale involved, and therefore the need to change configuration reliably at scale, the challenges we overcame to ameliorate larger issues triggered by config changes, the challenges we overcame to drive broader adoption of our protection mechanism, and the future work we have planned to make config changes even safer and faster. So first, we'll cover the early days of config change safety. Let's dive into configuration management. Configuration management at Meta comprises many powerful tools, one major platform being Configurator. As depicted here, engineers can use Configurator to update configs and see those updates reflected across our million-plus server fleet in a matter of seconds. Due to that feature set, Configurator operates at a very high scale. Over 99% of the thousands of services at Meta leverage Configurator for runtime configuration. And thousands of employees regularly make configuration changes, to the point that combined with automation, we see multiple sets of changes per second at peak. There is sometimes risk to making config changes, though. Just like engineers can roll out a config change to toggle a feature in a matter of seconds, we can also make a config change that uncovers a bug in that same time frame. Due to that risk, reliably changing configuration at our scale is one of Meta's primary strategies to prevent reliability issues. So, how do we make changing configs reliable and scale that up to cover all the uses we talked about? We give people the ability to test their changes. Making changes reliably starts with a simple approach. We give developers the ability to exercise their changes on a subset of the target. Not only does this allow them to test their changes on a sandbox environment, but gives them the ability to exercise their changes on real workloads, to catch bugs that may not be present in those sandbox environments. Let's walk through an example of how I would test my change with this functionality. Let's say I'm changing a config, foo_baz, and I'm setting the value of a to 2. I expect this to be used by service A, and instead of making my change on all 12 boxes of service A, I'm going to override my change on a single box, box number 3. I'll let it bake for a little while so that service A can use it, box 3 can go through some workflows, and I'll monitor the important metrics of service A, and then compare those on box 3 versus the other boxes to see how my change affected things. After some time, I notice it looks like it caused a regression. Luckily, it only regressed 1/12 of the workflows coming in, but I better remove the override and fix the issue. While this was a step in the right direction, this process was complex, prone to knowledge silos, and tedious. It required authors to know where their change could trigger a breakage, and override the change there. They needed to monitor the important metrics of the target, and they needed to wait for enough signal to deem their change safe, or even start this loop over again with a broader target group if the first one didn't provide enough signal. This process would not scale to meet our needs, so the obvious next step was to automate it. Services are unique at Meta. Their definitions of health differ, their scale differs, and their config usage patterns differ. So our automation needs to account for those differences. Such a system then needs information about these specifics, like we use during our manual testing. Things like, what set of machines should we run on? What % of the target should we override our test on? How much time does the override need to bake in order for us to gather enough signal? And what metrics and values should be used to indicate if the target is healthy? This information is provided in a structured test plan we call a Canary spec, which our Canary service can follow to test a config change set on a given target and a service. This reduced a lot of the manual repetitions of testing, busy waiting for signal, and knowledge gaps of which metrics to check. However, it still required developers to know which Canary specs to run for their change set and manually start them during their change workflow, So we fixed that. Even with hundreds of services, determining where to test a config change is challenging and subject to change. So we asked service owners to give us the list of configs that should trigger a run of their Canary spec. In doing so, this allowed them to enroll in our new system, AutoCanary, in addition to the config change workflow that will automatically canary with the following strategy. It will gather the names of the configs being changed and use the list provided by service owners to find the Canary specs we should run. From there, it'll run the Canary specs in parallel with one another. And if every Canary indicates the underlying targets are healthy, then we allow the change to roll out. Otherwise, we block it. While this is a leap forward, services still needed to enroll in AutoCanary to gain its protection. Over the handful of years following AutoCanary's creation, we made some enhancements but largely kept the enrollment process the same, and services onboarded organically, giving us the adoption curve depicted here. We focused on scaling up other aspects of Configurator throughout those years, but after some more exploration in the change safety space, we came back to see if we could improve the AutoCanary adoption process and protect more services from unsafe changes. Which brings us to the next chapter in our story, ameliorating larger-scale reliability issues triggered by config changes. So, let's solve the largest pain point of AutoCanary adoption. Our observations showed the manual process to specify and update the list of configs to test on a spec was the largest blocker. Asking humans to manually find all the config names is complicated and inaccurate. Services can use libraries, which themselves use configs. Therefore, a library's config change could trigger a breakage on the service itself. Asking service owners to find each of those configs manually is complicated and inaccurate. It's also high maintenance. Consumption patterns frequently change for an individual service. Asking humans to keep that list updated is a pain point, and if those lists aren't updated, they become inaccurate. Some power users even began independently working to automate this process for their services. So how do we scale up this manual process? Let's take a step back and go through a thought exercise. The picture here depicts a service's config consumption patterns. What services are at risk of breaking if BazFoo uncovers a bug? Pause this video, give it a thought. All right, let's resume. Service A and Service C. In general, config changes are a risk to those services which consume them. So we enhanced AutoCanary's enrollment to solve these pain points from earlier, with config consumption patterns in mind. Let's simply ask service owners for the name of the service they want us to protect from bad config changes, and the Canary spec that tells us how to test on their service, and we'll take care of the rest. We evolved AutoCanary to track the config consumption patterns of millions of servers in our fleet, a scaling challenge in its own right. Now when someone goes to make a change to configs, we gather the names of the configs being changed. We then look up the services that could be impacted by the change, those that consume the configs. And of those services we should test, we obtain the Canary specs for those which are enrolled. We then run those Canary specs in parallel with one another, and if every Canary passes, then we allow the change to be rolled out. Otherwise, it's blocked. After enhancing AutoCanary, we decided to invest further in our internal infrastructure's maintainability and reliability, so we can move faster. AutoCanary grew organically throughout that time, as shown here, and as we closed out that aforementioned investment, we pivoted a good chunk of our team back to focus more directly on changing configuration more reliably. As AutoCanary was already a standard part of the config change workflow, adding more coverage was a high-leverage mechanism to make config changes more reliable. So we decided to continue our AutoCanary work with one minor change. Instead of allowing AutoCanary adoption to happen organically, this time we decided to take matters into our own hands and drive adoption. So with thousands of services to onboard, where do we start? We're looking to prevent larger issues triggered by config changes. So we focused on adding protection to the subset of services that could trigger a larger issue when broken. Around that time, we were removing onboarding blockers. We observed larger issues were being triggered by config changes more frequently. So Meta quickly responded to this challenge, deciding to bolster our config change safety with multiple strategies, one of which pertains directly to the areas we've discussed so far. We decided to enroll the subset of services that could potentially trigger a larger issue when broken into AutoCanary. Doing so will ensure services have a strong mechanism to protect them against breakages triggered by bad config changes. We decided to expedite our AutoCanary adoption plan through many means, some of which were to scale AutoCanary and its dependencies to support more growth, improve our AutoCanary workflows, and scale out our other manual onboarding processes, like Canary spec creation. Specifically, we built tooling to automate the Canary spec creation process, so service owners simply need to run the tool with their service name, and the tooling would generate a spec and enrollment with all the required fields filled in. This made it so that service owners didn't need to spend time researching each field, finding the value to put in, and then doing the validation themselves. This default spec could be tuned to improve its signal and ensure the service had some protection against breakages triggered by bad config changes. With tooling in hand and collaboration across our org, we accomplished our goals in a short time period and boosted AutoCanary coverage by 2x. Since then, we have observed a downwards trend in the proportion of large issues triggered by config changes, prevented what may have resulted in a larger issue, and observed no further issues of that caliber triggered by Configurator config changes. That concerted effort drove adoption growth much faster than an organic approach of times past. And we accomplished our goal. So what's next? Protecting services that could trigger a large issue when broken. If we're just trying to eliminate issues triggered by config changes, there is a simple solution. Just stop all config changes. Then there can't be any issues triggered by config changes. Easy, right? Well, developers need to make config changes in order to mitigate issues and do their daily work. And a major part of reliably changing configuration at scale is to avoid unnecessarily impeding the developer and config change workflow with our protection mechanisms. Not just because it's important developers can make config changes, but we also observe that too much friction can impact the usage of AutoCanary, potentially resulting in an issue that may have been caught with AutoCanary. We could increase AutoCanary adoption by hundreds more canaries to protect against more classes of issues, but our earlier 2x increase in adoption impacted the developer experience. Additional adoption could further impact the developer experience. We need to strike a balance between adoption and developer experience. So let's dive into why an increase in adoption can impact the developer experience. We're going to take a step back to talk about canaries. We get the benefit of testing config changes on the exact workloads we see in production, so we can catch corner cases that may not be exercised in the sandbox environment. As a result, we also get non-determinism. So every canary spec will have at least some bit of flakiness, wherein the canary spec exhibits a false positive, where it blocks a safe change. This can be expressed with a conditional probability of a canary spec passing or failing when a change is safe. When the probability of passing when a change is safe doesn't equal 1, then that means the spec is somewhat flaky. Now we're going to talk about AutoCanary's decision logic. All specs selected by AutoCanary need to pass in order for the AutoCanary to pass. If even one fails and signals this change is unsafe for the service, then AutoCanary blocks the change. Therefore, the chance of AutoCanary passing on a safe change is equivalent to the product of each of its individual canary specs passing on a safe change, as denoted by the equation on the bottom of the slide. While driving up adoption accomplishes our end goal of increasing the percent of services we cover, it also increases the average number of canary specs that run during AutoCanary. Since every spec is at least the slightest bit flaky, increasing the number of specs run on average decreases the chance of AutoCanary passing on a safe change, as seen in the equation from our earlier slide. That can impact the developer experience, and this is better known as the multiple comparisons problem. So how do we get a handle on the multiple comparisons problem? Let's use a hypothetical example. Assume before broad adoption, AutoCanary would run the 3 specs with the hypothetical flakiness seen in the top left image for our change set. If our change set is safe, the chance of passing AutoCanary with those specs' hypothetical flakiness is 86%. If we drive up adoption, and that results in AutoCanary selecting 3 more specs for our change set with the flakiness seen in the bottom left image, then if our change set is safe, the chance of passing AutoCanary with those specs drops all the way down to 23%. At that point, you'd have a better chance of flipping 2 coins and both landing heads than AutoCanary passing on that change. What can we do to improve our chances of AutoCanary passing without sacrificing too much of this important coverage? Pause this video now and jot down your proposals. Alright, let's talk about a solution we pursued. As you may have noticed, there is only one canary spec that has a much lower chance of passing than the others, Spec 5. So what if we skip Spec 5? Cutting out that one spec shaves off 70% of flakiness and increases our chance of passing on a safe change from 23% to 76%. Let's turn this theory into practice. We'll need to fulfill the following requirements. We need to measure the chance a canary spec passes on a safe change to know if we should skip it. We need to react quickly to changes in flakiness so we could accurately reflect production. Otherwise, we might run a spec when it's flaky, or skip when it's healthy. Lastly, we need to support all specs that could be enrolled in AutoCanary. We have thousands of services, so it's safe to assume that we'll need to support thousands of canary specs. Let's dive into how we'll accomplish each requirement. I pose this question to you. What is a change that is always safe? one that will never break a target, a config that's never consumed. So, to determine if a Canary spec passes on a safe change, we simply run it on a change set that contains a config which is never consumed, and check if the Canary passes or fails. Alright, next requirement, reacting quickly to changes in flakiness. The white line shows Spec 1's true probability of passing on a safe change over time. Colored boxes indicate our measured value of passing on a safe change. When the box is orange, we'll skip the Canary spec, and when it's green, we'll run it. In our example depicted at the top, we run infrequent tests. As a result, we don't react quickly enough, so there's a large time period where we run the spec even though it's flaky. Then, when it goes healthy again, we continue to skip it for a while. In our example depicted at the bottom, we run tests more frequently. As a result, we react quicker, and run the unhealthy spec less frequently, and skip less frequently when the spec becomes healthy again. The more frequently we run our tests, the more temporally accurate our estimate will be, so we should perform our tests continuously and frequently. Lastly, how do we support thousands of Canary specs? We can't manually do all these tests continuously. We needed to build automation to scale this process. So we created Canary Spec Doctor, a service to continuously measure the flakiness for every spec enrolled in AutoCanary. Canary Spec Doctor will continuously retrieve the set of Canary specs enrolled in AutoCanary. Then, for each spec, it will run the spec with a never-consumed config to determine if it passes on a safe change. After that, it'll look back over a window of these runs to determine an aggregated passing rate. And if that pass rate exceeds a threshold, we consider the spec healthy. Otherwise, we consider it unhealthy. Among other actions, we integrated that spec health information into our AutoCanary workflow. AutoCanary retrieves the set of specs it should run based on the consumption data. It then consults the spec flakiness info to determine which specs are healthy. And then of those specs that are healthy, it runs, and of the ones that are unhealthy, it skips. While we can directly reduce AutoCanary flakiness by skipping specs, we shouldn't skip too aggressively or we'll reduce our coverage and risk missing an unsafe change. So, what were the results of tackling the set of flakiest specs? Well, since the system was productionized, we've only observed one large issue that may have been caught with the skip spec. But the system reduced the average failure rate of individual Canary runs by over 3x, and shaves off over 60% of flakiness on average for AutoCanary runs it applies to. Over that time, we had a hybrid, organic, concerted adoption effort going to keep high coverage for the services that could trigger a larger issue when broken, and allow other interested services to onboard if they wanted to, resulting in a less drastic adoption slope, but not for long. Now that we've implemented Canary Spec Doctor and other UX improvements we unfortunately don't have the time to cover today, we can move on to drive up coverage. Should we perform another event to drive up coverage? New services are constantly being created. If we only did that one manual effort, the number of services onboarded would go up initially, then flatline, whereas the number of total services would continue to increase over time, resulting in an inflationary process that would drive down our total coverage over time. Let's scale up a human process once more. We built automation to constantly look out for new services and run all the tooling we talked about earlier from our initial AutoCanary adoption event. With that automation in place, new service owners only need to act the generated spec and enrollment to gain AutoCanary protection. Nowadays, over 80% of services that could trigger a large or larger issue when broken are protected with AutoCanary. We expect this percentage to increase as we close our initial push and then roughly stay constant as new services are created and automatically onboarded with the system. We're mostly caught up to present day now. So, what's next? Our journey is only 1% finished. As more developers join Meta, they'll make config changes, and we'll create more services that use configs, so maintaining the status quo is not enough. We need to move safer and faster. We accomplished our goal of driving up coverage to get some protection for our services. Now, further improvements to the quality of that coverage will improve the protection of thousands of services and developer experience of thousands of change authors. In addition to improving the quality of the adoption process, we're invested in improving the Meta developer experience directly and safety directly. We'll accomplish this with projects like a better Canary Spec Management UX, automatically improving the quality of Canary specs and health checks, and onboarding more use cases to our other product offerings, and more. But that's not all we plan to do. There is an inherent trade-off between developer experience and safety. We can onboard more services and make stricter health check metrics to improve safety, but that could increase flakiness and slow down the developers. We could set a more aggressive flakiness threshold to consider specs unhealthy sooner, and skip more to improve the developer experience, but that could decrease our safety. We will improve each, but those efforts may take time to roll out. So, to improve developer experience or config safety ASAP, We're building a principled mechanism to gauge and act on the risk of a config change to balance the two. As you saw, scaling our protection mechanisms to cover the changes consumed by thousands of services at Meta is vital to our reliability. Doing so while maintaining a high-quality developer experience is even more important. So, if you like the challenge of making config changes safer and faster at our scale, then come join Meta. Lastly, I would like to thank my teammates and our partners who made this journey possible. And thank you for joining me on this journey of AutoCanary adoption.